All right, for those of you tuning in on the video, I forgot about the first 5-10 minutes. So we rehashed partial pressure, Boyle's law, and we're going over, after you calculate partial pressure, so that's what you use to calculate or figure out the concentration gradient for diffusion of oxygen. So we're going through the oxygen levels in different areas, the atmosphere, the alveoli, and different parts of the body. We plop the slide up. It was Emma's fault. All right, so out in the atmosphere, let me enlarge that again, make it a bit bigger. There we go. So that's the partial pressure of oxygen in the atmosphere, your inspired air. You breathe it in, and if you sample the air in your alveoli, it's 104 millimeters of mercury, give or take. That's a third lower than it was in the atmosphere. So we're just talking about the inefficiencies of a human's respiratory system. Mammals don't have a good respiratory system. It's time of breathing. You suck fresh air in the same opening, you get rid of the old stale air, and there's mixing. So you're mixing that inhaled air, which is nice and fresh, you're mixing with the old stale air. That is responsible for most of this drop, so it's really inefficient. So as I was saying, at the top of Mount Everest, a human can barely function, but there are birds. You know, like when you hear about jets, passenger jets striking birds once in a while, they're losing eggs and things like that. Those are often geese. There's a bar-headed goose that it migrates from pole to pole, every year, and their flight path is over Mount Everest. So typically what you have is a human at 29,000 feet on the top of Mount Everest, barely alive, 1,000 feet above them, they're bar-headed geese. Not only are they alive, they're flying. That's really energetically costly. Bird respiratory systems are way better than a human's. They don't have a lung like us. They're just, it's tube-like, it's one-way flow, much more efficient. But mammal lungs, not so good. So part of this drop in partial pressure is, again, just due to mixing fresh air with old air, and you lose a bit of that. The other thing that dilutes this is when you inhale air, what are you adding to it? Remember we looked at the nasal cavities? Atmospheric air can be fairly dry. When you add water vapor is a gas. So when you inhale, you're adding water vapor. That takes up some of the space, so you're actually diluting the oxygen a bit more. In fact, water vapor is a little weird. It's not a big deal, but water vapor is a gas. It exerts a partial pressure like any other gas, but it does behave a little differently. If you look at the air in your lungs, it is saturated with water vapor. That is, it's at 100% relative humidity. The partial pressure of water vapor in your lungs is 47 millimeters of mercury. In the atmosphere, it's insignificant. So of that, whatever the total pressure is, say 760, in your lungs, 47 millimeters is just water vapor. So that water vapor you're adding actually takes up some of the space. It kind of dilutes the oxygen a bit. That explains a little bit of this drop. The reason this is interesting, most other gases we've looked at, if you change the atmospheric pressure, you'll of course change the partial pressure, right? Oxygen, CO2, nitrogen, that's true. That is not true of water vapor. As long as you have gas that has 100% relative humidity, that is, it's saturated with water vapor pressure is only dependent on the temperature. So at 37 degrees Celsius, which unless you're dead, your body's going to be 37 degrees Celsius, the water vapor pressure is always 47 millimeters of mercury. Now, at sea level, is that a big deal? No, 47 out of 760 millimeters of mercury, it's not a huge fraction, not a big deal. What if you go up in elevation? Let's just say, for the sake of argument, you go up in the old Concorde, those supersonic transports, they'll fly up close to 50,000 feet. Or you go up in, what is that, Virgin Galactic's new passenger orbiter or something. Let's say you go high enough, so you're at about 50,000 feet. The total atmospheric pressure at 50,000 or so feet is 47 millimeters of mercury. Of course, you couldn't survive in this. Well, let's say your airplane at 50-some thousand feet depressurizes. You're going to be sitting there trying to breathe. You're going to be ventilating. But what's in your lungs at 57,000 feet or so? If the total pressure is 47 millimeters of mercury, the partial pressure of water vapor at your body temperature is 47 millimeters of mercury. What's in your lungs? Nothing but water vapor. So the person will look like they're ventilating, but they're not. All they're doing is they're exhaling water vapor. When they try and inhale, they're not actually inhaling anything. The water in the lungs just evaporates to fill up the space at 47 millimeters of mercury. So all we're doing is outgassing water vapor. You die really, really quickly at these pressures. But the sort of point I'm trying to make is, as the pressure gets lower, water vapor takes up a larger and larger fraction of what's in your lungs. It's another problem at high altitude. At top Mount Everest, when the total pressure is 220 millimeters of mercury, you're getting close to almost a fourth of the partial pressure is due to water vapor. That takes a lot of space. So that's actually a fixed value as long as your body temperature is 37 degrees. So it becomes important as pressures drop. But anyway, you get that drop in PO2 just by inhaling the air, mostly because of the inefficiencies mixing fresh air and old air. And a little bit of this drop is due to you're adding water vapor, which also dilutes the oxygen. Now, the rest of these partial pressures, once with the alveoli, of course, that's kind of it for the lungs, but I'll go a little lower. In the lungs, the gases in your lung will basically reach equilibrium with the blood in the pulmonary capillaries. Your lung is very efficient at diffusion, so you're going to reach equilibrium. So if you sample the blood leaving your lungs, say in the pulmonary veins, this is what they're calling oxygenated blood. And it doesn't matter if it's pulmonary veins or systemic arteries, they'll all be the same, because the pulmonary veins, systemic arteries have the same amount of oxygen. So when we get to the arterial blood, typically I'm talking about systemic arterial blood, what you find in the aorta, that sort of thing. It's the same as what's in the pulmonary veins. The PO2 is about 95 millimeters of mercury. Now, I told you reached equilibrium. You do, but 95 is not 104, is it? So why is there a difference? That's not because of a deficiency in diffusion. I don't know if you remember when we was talking about the smooth muscle in the airways, how you have to have ventilation perfusion matching, that is, send the blood to the same place you're sending the air, right? Well, that's not 100%. There are portions of your lung that you perfuse, you send blood to, but you aren't ventilating currently. That means they're dead, stale air. That blood does not pick up any oxygen. Even though it reaches equilibrium with the gases in the alveoli, the oxygen's already been depleted. So that's why you see a bit of a drop. This is not, that drop from 104 to 95, that's not a significant drop. It's not due to any inefficiencies in diffusion. It's inefficiencies in basically ventilation and perfusion, where you're sending everything is not quite 100% max. This drop is insignificant. I mean, if you call that 100, that 100, I probably would mark it wrong. It's a really small drop. But again, even if the oxygen is in liquid, in the blood, you still measure its concentration by partial pressure. In fact, if you're doing a lot of blood work down the road, you might see this listed as PaO2. That's a notation. What that means is partial pressure of oxygen. A is an abbreviation for arterial, systemic arterial. And you'll see that in a lot of more detailed blood work. They usually, if you're just going in to get a checkup, they don't do gas-tight samples of your blood. But if they suspect there might be an issue, they will take gas-tight samples, and they'll look at the partial pressures in different areas to see if there's a deficiency somewhere in your lungs, in the diffusion, or what have you. And we'll measure partial pressure in the blood as well. That's still what uses concentration. Now we're going to take this arterial blood down the aorta. Let's say we send it down to the muscles of your leg or something. Of course, the oxygen levels don't change while they're in the arteries because there's nothing being exchanged. Then we get down to the tissues. Of course, the tissues are where you want the oxygen. Tissues are constantly consuming the oxygen, right? This is where metabolism is occurring. So the electron transport chain is constantly taking the oxygen, converting it into water, to dump off extra electrons and hydrogens. So if you look in the tissue fluid, so not the blood, but just the extracellular fluid, the interstitial fluid around the tissues, if you sampled it, the PO2 is quite low. Which you'd expect. This is the lowest point in the system because this is where you're using it. So tissue PO2 is about 40 millimeters of mercury. And I will tell you that is an average. It depends on the tissue. It can range from 15 to 60 or so. So tissues, the PO2 you'll find in a particular tissue depends on its activity. An exercising muscle, the PO2 may drop down to 15 millimeters of mercury. Another area where you're not using hardly any metabolism, where metabolism is quite low, that might be 60. So that's an average. If you kind of pull all the blood draining from all your tissues, mix it in a bucket, sample PO2, it'll be about 40. And I will tell you, as the blood moves through the tissues, it does reach equilibrium. So the blood coming in has a PO2 of nearly 195. The tissue's got a PO2 of 40. As the blood passes through the capillaries, of course, the oxygen is going from an area of high PO2 to an area of lower PO2, and it does reach equilibrium. So if you sample the venous blood, that is the blood draining the capillaries, it's also about 40 millimeters of mercury. It's the same as it is in the tissues. You have to reach equilibrium. That is the blood that's going to go back to the lungs. So this blood coming into the pulmonary capillaries, it's got a PO2 of 40. The air in the alveoli has a PO2 of 104. So I'm going to put one more thing down here. This will be, draw a line here. Delta PO2. What I'm asking is, what is the partial pressure difference causing oxygen to move from the alveoli into the blood? Make this a little smaller. So this used blood, in quotes, had a lot of oxygen diffused out. The PO2 is 40 in this blood, right? This is the blood that's making it back to the lungs. So the PO2 of this blood entering the pulmonary capillaries is 40 millimeters of mercury. That's its PO2. So that's the blood that's surrounding the alveoli. In the alveoli, the PO2 is 104. So the concentration difference allowing oxygen to diffuse from the alveoli into the pulmonary capillaries is, what is that, 64? Right, does that make sense? That's your concentration gradient. So you got a PO2 of 104 in the alveoli, the blood coming in has a PO2 of 40. So there's a partial pressure gradient of 64 millimeters of mercury, basically pushing the oxygen from the alveoli into the blood. Now remember that, because now we're going to look at another gas. So those are just kind of the points, around the sort of respiratory and circulatory system. Let's do the same, yeah.
So partial pressure.
Gradient or difference for O2 is 64 between the lungs and the blood. This is actually what we're looking at. It's this one and this one. That's this difference across the respiratory membrane. Does that kind of make sense? All right. Now, just given that, we'll go into it. Let's look at carbon dioxide, because carbon dioxide, something similar is going to happen. But keep in mind, carbon dioxide concentrations, relatively speaking, are going to be reversed. The CO2 is produced in the tissues, that's where it's going to be highest, and you get rid of it now in the lungs, so it's going to be lowest in the atmosphere. So the direction it's diffusing is different. But we'll go the same way. All right, inspired air. The partial pressure of carbon dioxide in atmospheric air, you can almost ignore it. It's 0.3 millimeters of mercury. See, if it's like, what is it, 0.03% or something, it's insignificant. So atmospheric PCO2 is 0.3 millimeters of mercury. So it's almost none, significant amount in the atmosphere. It's pretty significant, except for that global warming stuff. Physiologically, 0.3% is fine. Then we go down to the alveoli, and look at that. Just inhaling in the alveoli, the PCO2 is 40 millimeters of mercury. That's a huge increase. So what is that, more than 100-fold increase? Huge. As we'll see, there's a reason for this. You're breathing. One of the reasons you breathe is actually to retain carbon dioxide. As we'll see in a bit, you're not breathing to control oxygen levels. They're almost irrelevant. You're breathing to actually retain carbon dioxide in your lungs and therefore in your blood. Let's run through the rest real quick. So the partial pressure of carbon dioxide in your alveoli is 40. As the blood moves through it, it reaches equilibrium. So if you look at the partial pressure of CO2 as the blood leaves your pulmonary capillaries, so that's, pulmonary veins or systemic arteries, there's really no change in the arterial blood. If you took a sample, 40 millimeters of mercury. Then we go down to the tissues. And of course, the tissues are the source of the carbon dioxide. So if you sample fluid around your tissues, because they're metabolizing, they're constantly producing CO2, the levels are higher. PCO2, carbon dioxide in the tissues, is 46. 46 millimeters of mercury. And of course, as the blood flows through it, we'll reach equilibrium in these systemic capillaries. So as the blood leaves the tissues, if you look at its PCO2, it's also 46 millimeters of mercury in the veins. And that blood is going to make its way back to the lungs. So the carbon dioxide concentration in this used systemic blood, we'll call it venous blood, is 46 millimeters of mercury. The PCO2 in the lungs is 40 millimeters of mercury. So the partial pressure gradient for CO2 is going to move the carbon dioxide out, right, from the blood into the lungs. But what's the concentration gradient? That is, what is the, call it the delta or difference in PCO2. That is, what's the partial pressure gradient moving carbon dioxide from the pulmonary capillaries out into the alveoli so you can exhale it? Well, you got 46 millimeters of mercury in the blood, you got 40 in the alveoli, that's a 6 millimeter of mercury difference, right? Pushing sort of the carbon dioxide or allowing the carbon dioxide to diffuse from the blood into the alveoli. 6 millimeters of mercury, right? Makes sense? All right. So that's going to be 6 millimeters of mercury. So those are just the concentrations of different areas. But what I want you to look at is those bottom numbers. All right, the concentration difference or partial pressure difference for oxygen is 64 millimeters of mercury. That is pushing oxygen from the alveoli into the blood. The concentration difference for carbon dioxide, moving CO2 from the blood to the alveoli, is only 6 millimeters of mercury. So you basically have about 10 times the concentration gradient for oxygen as you do with carbon dioxide, right? Round it off a bit. So here's where it gets kind of weird. So if you had to guess, just knowing that, which one do you think, in a minute, do you think you move more oxygen across the respiratory membrane from the lungs into the blood, or do you move more CO2 from the blood? Which one do you move more of? Remember, what are factors that affect rates of diffusion? We've looked at things like distance, right? Surface area, concentration gradient. Well, the respiratory membrane is the same thickness for both gases, right? The molecular weight of oxygen and carbon dioxide is pretty darn close. That's not going to account for that. If you look at those numbers, which one are you going to guess you move more, oxygen or carbon dioxide? I guess oxygen, right? You got 10 times the concentration gradient. Everything else seems to be the same. That is, if you look at this respiratory membrane, CO2 is moving this way from the blood into the alveolus, oxygen moving this way. They're going across the same membrane, same distance, molecular weight's pretty darn close, temperature's the same. The only thing that looks different is the concentration gradient. So just look at those numbers, yeah, I'd say you gotta be moving more oxygen than CO2. You're not. It's kind of weird. It turns out you move almost exactly the same number of oxygen molecules across the respiratory membrane as you move carbon dioxide molecules. In fact, I'll put an example up here. You have to move about the same number of oxygen and CO2 molecules. Why? Do you remember this equation from last semester? You did something like this. You got C6H12O6 plus 6 oxygen molecules produces 6 CO2 molecules plus 6 H2O molecules. This was a net equation they gave you last semester for cell respiration, right? Except they had something like this, you made 38 ATPs, something like that. That's not respiration. That kind of ring a bell a bit. You take your glucose in the presence of oxygen, you burn it up, break it up, produce carbon dioxide and water as an end product, and you assemble like 38 ATPs. Okay? The only place you're using oxygen in your body is where? Right here. This is it. You only need oxygen in the mitochondria, in the electron transport chain. That's the only place you use it. The only place you produce carbon dioxide, this waste gas, is in the same metabolic pathways. But look at this balanced equation. If I burn up 6 oxygen molecules, I produce 6 carbon dioxide molecules. What that means is it's a 1-to-1 relationship. All right, there's a couple of caveats here. This assumes you're only eating carbohydrates, so that's what we'll assume. But it's 1-to-1 if you're just eating carbohydrates, which means every time an oxygen molecule moves across, you basically have to move an equal number of CO2 molecules across. It has to be 1 for 1 because this is the place they're coming from and the place they're going, and it's 1 to 1. So what looks weird then here, how is it possible that you're moving the same amount of oxygen as carbon dioxide when you got 10 times the concentration gradient for oxygen compared to CO2? But it is true. Across your lungs, you move about the same amount of oxygen as CO2. They move opposite directions, but it's about the same number of molecules. That is because, here's the last gas law I mentioned. There's one thing that we kind of skip over a lot of. We were talking about diffusion, and that was is not important, it just muddies the water. But there is something called, that affects rate of diffusion, called solubility. You know, we all kind of know what solubility is. It's actually hard for me to describe it really, but everyone kind of conceptually knows a bit about solubility. Solubility is how well something sort of dissolves in something else, right? We're more familiar with it with liquids and solids than we are with gases, but it's the same thing. That's like saying if I took vegetable oil, 100% vegetable oil, and put it in a container of water. So if I look at a beaker, here's a beaker of water, and I put a glob of vegetable oil in here. All right, there's 100% vegetable oil in this glob. There's 0% vegetable oil down here in the water. Is this vegetable oil going to diffuse down there? It doesn't. Why not? It's a concentration difference because vegetable oil has really no solubility in water. So this is kind of what we're talking about with gases. Let me give you another example because, again, we're used to looking at, I think, solids and liquids with water, for example. We understand solubility a bit. If I took table salt, sodium chloride, and I put a teaspoon in a cup of water, will it dissolve? Yeah. I took a second teaspoon, dump it in there. Will it dissolve? Yeah. A third. Yeah. How many? I'm not really sure. Well, you can put a bowl of salt in water. Salt, sodium chloride, is very soluble in water. Now, eventually what will happen if you keep putting salt in water? Eventually reach a point where you've saturated the solution, and so no more salt will dissolve, or if any more salt dissolves, you'll start getting salt depositing as crystals in the container, right? But salt has a really high solubility. I think you kind of know that, right? Because you can dump it in water, it dissolves right away stuff. What about calcium carbonate? That's the rock out here, like you might have in your driveway, or most of the rock around here is calcium carbonate. Is it soluble in water? All right, here's where it gets a little iffy. If you took a teaspoon of ground calcium carbonate, this is what farmers put on their fields, by the way. The ag lime they're putting out is just calcium carbonate rock ground into a fine powder. It is soluble in water. But if I took a teaspoon of ground up limestone and poured it in a cup of water, some of it would dissolve, but probably not even a teaspoon. It's soluble, because you ever been like, what is that, frozen Niagara, Mammoth Cave? You ever been in there, or any cave formation? You know what that's made out of? Calcium carbonate. Around here, the rainwater hits that limestone. It actually dissolves some of it, goes through the ground, but it comes out in the cave and the water evaporates. That's leaving behind calcium carbonate. Or, now you do this, but have you ever taken a pot of water to like cook something or heat something up, and you put the water on the stove and you kind of forget it and like leave for like an hour, and all the water evaporates in the pot? But you haven't quite melted your pot yet, it hasn't been that bad. You'll notice a white film around your pot or something. That's calcium carbonate. We have a lot of it dissolved in the water here because all of our rock is limestone pretty much. So it is soluble, but not as much. So that's kind of the idea. You can have substances, it's not you're soluble or you're not. There's different levels. Sodium chloride, that salt, is really soluble in water. Calcium carbonate, it is still soluble in water. It's just not very much will go in the water and then it starts to precipitate out quicker. It's not as soluble. So gases are the same way. So let me give you my gas example. What I'm going to do, let's say I'm going to set up a little aquarium here. And I'm going to half fill it with water. And I'm going to hook it up to a gas bottle, which is pure oxygen. And I'm going to run this oxygen into this tank. Now what I start with initially is half of this is gas phase, half of it's water. The water has an initial PO2 of nothing. So I put oxygen in here until I get a partial pressure of oxygen that equals 100 millimeters of mercury. So I start off with a partial pressure gradient. I got a PO2 of 100 in the gas phase, and I got a partial pressure of 0 in the water. So the oxygen's going to diffuse from the gas, it'll diffuse into the liquid and dissolve, right? Does that make sense? It's a concentration. It will. And I'm going to use these little blue dots to represent oxygen molecules that move into there, because 10 little blue dots in there. That's the oxygen that diffuses in. But just like salt, will the oxygen keep diffusing in? When does it stop diffusing in? Well, when does diffusion in general stop? When you reach equal concentrations, right? Right, same thing happens here. The oxygen will diffuse into the liquid phase until the partial pressure in the water is the same as the partial pressure in the gas phase. So once diffusion will stop when the PO2 is equilibrium, just like you looked at before. 100 millimeters of mercury in this example. That kind of makes sense. It's not different. You get diffusion until you reach equal concentrations. In this case, our concentration measure is millimeters of mercury. But here's my next question. Where are there more oxygen molecules? In this half, that's nothing but oxygen, or in this half, that's oxygen mixed with water? Do you think there's equal number of oxygen molecules in both those spaces? It doesn't really, most of this volume is taken up by water. All this volume is nothing but oxygen. There is going to be a difference in the number of molecules. This is where solubility comes in. Every time an oxygen molecule dissolves into the water, it ups the partial pressure. But as we'll see, oxygen is not very soluble in water. So really, after just a few oxygen molecules diffuse into the water, the partial pressure is 100. Now, again, movement still works, but if another oxygen molecule moves in at this point, one of them is going to likely move out. So it's just like with that salted water. Once you put enough sodium chloride in water, if any more sodium chloride dissolves, it starts precipitating back into a solid in the walls, makes those crystals. Same things here. There's only so many oxygen molecules you get in the water, and you reach that PO2 of 100. Now, solubility is tricky mathematically. I don't understand it, so you're not going to have to. It's just kind of a relative measure for us. But now let's look at CO2. I'll give you a similar example. This time I'm going to take a gas bottle, but this one's carbon dioxide. And I'll do exactly the same thing. I got a container, it's half filled with water. The PCO2 initially equals 0. I'm going to let CO2 into this gas phase until I have a partial pressure of CO2 of 100 millimeters of mercury. And just like oxygen, you have a partial pressure gradient, so CO2 is going to move from the gas phase into the liquid phase until we reach partial pressure equilibrium. However, I will tell you, carbon dioxide is 20 times more soluble than oxygen. That's the only number I'm going to give you, because otherwise this gets too complicated. So carbon dioxide has a higher solubility in water than oxygen, about 20 times more soluble, which means CO2 is going to diffuse into the water until the partial pressure of carbon dioxide is 100 millimeters of mercury. But in order to get there, a whole lot more molecules have to dissolve in. In fact, how many more? I'd be twice as many, but I'm going to stop there. I have 200 dots here. Even though the partial pressures are the same now, we've reached equilibrium here with oxygen, PO2 of 100, PO2 of 100, PCO2 of 100, PCO2 of 100. In order to get there, 20 times more CO2 molecules diffuse from the gas into liquid. Why? Because CO2 is much more soluble. What this means in your body, your blood, your tissues are basically water. It's much easier to move carbon dioxide. Another way of looking at it, for each 1 millimeter of mercury partial pressure difference, I will move 20 times as many CO2 molecules as I would oxygen molecules. So if you have like a 1 millimeter of mercury pressure difference, I might move, 1 oxygen molecule from the gas to the liquid. At the same 1 millimeter of mercury CO2 pressure difference, I move 20 oxygen molecules into the water before it got to 1 millimeter PCO2 in the water. That kind of makes sense? This is called Henry's Law, although we won't look at it formally because, again, solubility is way too complicated because everything affects it. But solubility is characteristic of the fluid and the environment. It's affected by temperature, the other ions dissolve, all kinds of stuff. But for our purposes, in human tissues and body fluids, CO2 is 20 times more soluble. So that gets us back to this difference here. Because CO2 is much more soluble, you don't need as big a concentration gradient to move just as many molecules. Oxygen, on the other hand, is very insoluble. It's not very soluble in water. So in order to move the same amount of oxygen as CO2, you need a much higher concentration gradient. That's why the partial pressure concentration gradient for oxygen has to be so high. It's because oxygen is really hard to move. CO2, it's easy to move. That's Henry's law. So here's what you need to know about Henry's law. What determines how much of a gas can move into a solution? There are two things. One is the partial pressure gradient, concentration gradient. The other is solubility. So two things determine how much of a gas will go in the solution. One is concentration gradient. The other is solubility. That's all you need to know about Henry's law. The question I'll ask you will literally be something like, what determines how much of a gas will dissolve into fluid? It might be water, it might be blood. Your answer will be partial pressure gradient and solubility. And what we know about carbon dioxide, it's 20 times more soluble, so you don't need as big a concentration gradient to move a lot of CO2. Does that kind of make sense? So CO2 is very easy to move. Oxygen is difficult to move because it's not soluble in body fluids, so you need to maintain really high concentration gradients. I'll leave that there. Does that make sense? That's Henry's law. That's the third gas law. Does that make sense? All right. It's just like, again, I use solids. If you had 2 cups of water and you had ground calcium carbonate and ground salt, salt is really soluble. Calcium carbonate is soluble, but not much. So if you put 1 teaspoon of each into water, the salt will dissolve. The calcium carbonate, only a bit of it will dissolve. Then you have solids sitting there, won't dissolve. It's kind of the same thing here. Because CO2 is much more soluble, it's very easy it'll dissolve in the water, in the blood really easily. Oxygen is not soluble, so only a little bit of it moves into the water, into the blood. If you get more in it, you have to make a bigger concentration difference. It's kind of all it means. So the amount of these respiratory gases that you can get in the liquid is determined by 2 things. Partial pressure gradient, that's the concentration difference. That's one. You gotta have that or nothing's gonna move. And the other is solubility. And again, for each system, solubility will change. That's why we're not, looking at it sort of generally. If everything is the same, we know in a human body, carbon dioxide is about 20 times more soluble. So that means for each 1 millimeter of mercury partial pressure gradient difference between the blood and your lungs, you can move 20 times more CO2 molecules than oxygen molecules, just because of the solubility. So if you want to move the same amount of oxygen and carbon dioxide, because of the solubility difference, you have to have a concentration gradient for oxygen. That's a whole lot bigger. That's why you see those 2 partial pressure gradients in the lungs are so different. CO2, easy to move. A few millimeters of mercury difference between the air in the lungs and the blood and pulmonary capillaries, that 6 millimeter mercury difference is enough to move a whole lot of CO2. For oxygen, because of its lower solubility, if you had just a 6 millimeter mercury difference for oxygen, you wouldn't move very many oxygen molecules. It wouldn't be enough to support your metabolism. So you maintain a much higher concentration gradient in the alveoli and the blood just to ensure you move equal numbers of oxygen and CO2 molecules, which you'll eventually have to do because they're produced and used in the same numbers. For every 10 CO2 molecules you produce, you burn 10 oxygen molecules. So you have to exchange the same number across between the lungs and the blood. In order to do that, because oxygen has such a low solubility, you need to maintain a really high partial pressure gradient. That's kind of all I was getting out with all those crazy numbers. All right. Last thing we'll do for the day we know your breathing pattern changes, right? Right now, you're half asleep, you're probably breathing 15, 16 times a minute. Every time you inhale, you only move like half a liter in, half a liter out. This is called tidal breathing. You're not moving much air. If you get up and start exercising, what happens to your breathing pattern? You breathe much deeper, you breathe much faster, right? So we know, I think just from personal experience, your breathing pattern changes with demand. When you exercise, you breathe a lot more. When you're just laying there half asleep, you're not breathing much. We know it changes. We know why it changes. When you're exercising, you need more oxygen and you're producing more CO2, so you need to exchange more across the lungs, right? So the respiratory and circulatory systems speed up when you exercise. That's certainly true. But my next question is, we know your breathing pattern changes, and we know breathing is due to skeletal muscles, right? The diaphragm and intercostal muscles, those have to be controlled by motor neurons coming from your brain. So I think it's a pretty simple leap to say when your breathing pattern changes, obviously your brain is sending more action potentials, the phrenic nerve that goes to your diaphragm, and I forget the one that goes to your calcium muscles, but it's controlled by the brain, right? It's a motor neuron that runs, and there's skeletal muscles just like others. So we know the breathing pattern changes, and we know it's the brain that makes those respiratory muscles either contract faster or slower. But here's my next question. Your breathing pattern, of course, doesn't change randomly. So my question is, how does the brain know to make you breathe faster under some conditions and slower? Again, we know the brain's controlling breathing, or just motor neurons. But what do you think the brain, it has to receive some information to know whether to make you breathe faster or slower, right? What do you think the information is that the brain has to monitor? It's got to be monitoring something to know, increased breathing pattern, our metabolism's up. What do you think it monitors? What do you think it's monitoring? The what? Oxygen levels. I like that answer because that's the intuitive one. It's not correct. It's kind of weird. We've been talking about oxygen. We don't need oxygen. Oxygen's important. It turns out our respiratory system, oxygen doesn't really do much of anything. It does control breathing. Why? It's also why our respiratory system, I mentioned earlier, it's kind of crappy in mammals. And it is. It's not a good system, from a design perspective, an engineering perspective. Our respiratory system is crappy. And we don't even use it to control, we don't breathe to control oxygen levels. Why? Because atmospheric air has so much oxygen in it, believe it or not. 21% is huge. We don't need a good respiratory system. In fact, there's so much oxygen, we don't even control our breathing to control oxygen levels. Because under ordinary circumstances, you got plenty of oxygen. So what your brain does monitor, it turns out there are two areas where you monitor characteristics of the blood. And that information, there's sensory neurons, that information is sent to the brain to control breathing. The two areas, in general, they're referred to as central chemoreceptors are in the brain. They're in the medulla, I believe. They're monitoring the characteristics of your cerebrospinal fluid primarily, which is pulled directly out of the blood. And you also have some peripheral chemoreceptors. Those are located not in the brain, hence that's why they call them peripheral chemoreceptors. Just give you a quick shot here. Remember in lab, actually you don't have to remember now because you're not testing on again, but here's those common carotids. Then your internal and external carotid. Here's the carotid sinus here. The reason I partly pointed those out in lab, inside the carotid sinus, or associated to it, right kind of where they split, there's something called a carotid body. That's a peripheral chemoreceptor. It's monitoring the chemical makeup of the blood as it goes towards the brain. You've also got some in your aorta. Down here it's showing you some sensory chemoreceptors. Again, these are peripheral, so they're aortic bodies, they're called. These are monitoring characteristics of the blood as it leaves aorta. So you got two sets of sensors. One's directly in your brain, we call those the central chemoreceptors, and then somehow not in your brain, they're in the carotid arteries, the aorta. Now it turns out, under normal conditions, I guess we call typical conditions, the central chemoreceptors are primarily responsible for controlling your breathing pattern. These will kick in under certain situations, sort of more severe situations, lower oxygen levels, things like that, really extraneous exercise. So it's mostly the central chemoreceptors. And it turns out what the central chemoreceptors monitor, they're not sensitive to oxygen at all, which is crazy. They monitor, hard to separate, and we'll play with that next time, but they basically monitor the characteristic, the CO2 concentration, and the pH of the blood. That's what they're more sensitive to. They're not sensitive to oxygen at all. And remember, this is what's controlling your breathing pattern. Again, part of the reason we're set up this way is there's so much oxygen available, we always get enough unless something really weird happens. So we actually shift to control CO2. Let me show you a diagram here, because this will show you what I mean. Let's just say, for the sake of argument, hold the screen out. This is kind of cool. This demonstrates, your breathing, how your breathing is controlled pretty well. That'll have to do. what you're seeing here, this is breathing rate. This is just ventilation. We'll look at it as a relative scale. You know, down here, you're breathing pretty slow. This, you're breathing faster. This is respiratory rate on the y-axis. Now, you got two different x-axes. We'll look down here first. This is a percent O2, and we're looking at the red line. Now, what this is telling you, let's say I can take this room and seal it so it's airtight, and I'm gonna go outside and look in the window. And what I'm gonna do is I'm gonna change the gas you're mixing. Right now, you're breathing, actually, right now, we're breathing air that is 21% oxygen. This is your breathing rate right here. You know, what is that? I don't know, 15 liters per minute, maybe a little less. But now I change the gas in this room. So I take it, instead of 21%, I start sticking in air that's only 18% oxygen. What happens to your breathing pattern? I just drop the amount of oxygen 3%. What's happened to your breathing pattern? According to this diagram. It's pretty much flat line, right? Which means nothing has changed. All right, I mix my gas bottles and I drop the air in this room down to 16% oxygen. What's happened to your breathing pattern? Nothing. You just lost 5% of the available oxygen. Your breathing pattern hasn't changed at all. I dropped some more. Now it's only 14% oxygen. What's happened to your breathing pattern? Nothing. I just dropped, what's that, 7% drop in the available oxygen? There would be no change in your breathing. I drop it down to 12. Ooh. Maybe at about half of the normal, volume of oxygen, you see a slight change in ventilation. I mean, we got to get way down here to, 8, 10, 6%, and your breathing goes up. So what this is telling you, if I change the amount of oxygen in your inspired air a few percent, does it really even matter? No, it doesn't matter at all. You're not sensitive to oxygen. So I can drop, the oxygen levels 8%, which is huge. It's a third of the available oxygen. Your breathing pattern won't change at all. And actually, the amount of oxygen in your blood is unchanged. Everything's fine. We're not sensitive to oxygen at all. On the other hand, the other axis up here, let me drop this down a little bit. This is the percent carbon dioxide in your inhaled air. We're going to watch the blue line. Note the scale is different. Each of these is a 1% change. Each of these with a 2% change. So what happens now, you're breathing air, everything's fine. We're at about, 0 CO2 for all practical purposes, 0.3 millimeters of mercury, and your breathing is just fine. Now, I up the CO2 in the inhaled air to 1%. Does that change anything? No. So 1% CO2, you can see no change in ventilation. Now I change it to 2%. Do you notice a bit of a change? Yes. Just at 2% CO2, your breathing pattern goes up. By the time I get to about 8% CO2, where's 8%? Sorry, wrong scale. Your breathing's about maximum. At 8% CO2, you just be pumping as fast as you possibly can. At 10% CO2, you're dead. So anyway, but maximal breathing about 8%. What this chart is just trying to show you, you are really, really sensitive to carbon dioxide levels in the air. You are not sensitive to oxygen, hardly at all. Only when it starts getting incredibly low, as we'll see, the peripheral chemoreceptors, they can detect oxygen levels. And if oxygen in the blood gets low enough, then you'll eventually kick in breathing just to get more oxygen. But normally, there's so much oxygen in your blood, you don't even bother to control it. Your breathing pattern normally is to control CO2. Why would you want to control CO2? All right, one last equation for the day. Because you may remember this one from last semester as well. All right. If you take carbon dioxide, CO2, and you put it in water, keep in mind in your body, water, there's always plenty of water, it's in excess. These two materials, these two molecules will spontaneously recombine and they'll form this thing here, H2CO3, which is called carbonic acid. This is a weak acid. This happens if you drink any carbonated beverages. This is what they've done. If you measure the pH of, Coke or Mountain Dew or Dr. Pepper, measure its pH, it's acidic. It's not because of anything else they've added. They're all carbonated. Beer would be the same way. If there's carbon dioxide in it, it's going to spontaneously combine with water, produces carbonic acid, This is a weak acid, which means it will partly dissociate, and you'll end up producing hydrogen ions right there, and this stuff right here with a negative charge, these are called bicarbonate ions. But remember, pH is a measure of hydrogen ions in solution. This equation is saying that carbon dioxide is an acid. By definition, if you add it to water, you will increase the hydrogen ion concentration. This is actually, under normal conditions, is what's controlling your breathing. You're controlling your breathing, control the amount of CO2. The amount of CO2 will determine your blood pH. This is what stimulates breathing. You know when you hold your breath, and you can hold it for like a minute or two, and that's probably about it. That overriding urge to breathe you get is not due to a lack of oxygen. As you hold your breath, yes, you're burning some of the oxygen, but there's still plenty of it. But as you hold your breath, you're constantly producing carbon dioxide. That's going to make your blood get more and more acidic. That's what your brain picks up. That overriding urge to breathe is because of the drop in pH due to the rise in PCO2. That's what gives you that overriding urge to breathe. It's not lack of oxygen normally. It's the buildup of carbon dioxide, which acidifies your blood. You're using your respiratory system to maintain your blood pH. By the way, blood pH usually about 7.35. If you hold your breath, your blood will become acidic. The pH will drop, 7.3, 7.25. That's what stimulates your breathing. It's not normally the lack of oxygen. It's the buildup of carbon dioxide because it's an acid. So that's your normal breathing pattern. It's got nothing to do with oxygen. Your breathing pattern is control your blood pH. Normally, if you control CO2 levels, you'll automatically have enough oxygen, so basically your brain by default doesn't worry about it because you're controlling for the right amount of CO2 and pH. You got plenty of oxygen, so there's no need to really monitor it that closely. That's also why, you know, people hyperventilate. You ever see them hyperventilate? That's really deep, rapid abnormal breathing. What happens to them eventually? They pass out. That's not through the lack of oxygen. They have the same amount of oxygen in their blood anyway. If you breathe really fast, they refer to that as blowing off CO2. Your normal breathing pattern, remember, PCO2 in the atmosphere is almost zero. PCO2 in your lungs is 40, and your blood is 40. You're breathing to maintain that high CO2 level. If you start hyperventilating, they refer to as blowing off CO2. You get less CO2 in your lungs, PCO2 in your alveoli drops, which means you get less CO2 in your blood. It's going to have the opposite effect. As you get rid of carbon dioxide, this equation goes to the left. You get rid of hydrogen ions, and your blood pH goes up. You get too basic, and that will cause you to pass out. If your pH shifts, your brain shuts off. So that's primarily what you're controlling your breathing for is to control CO2 levels and therefore pH. Now, we don't have time today, but in emergencies or odd situations, you will breathe if O2 levels get low enough, and that actually causes weird issues with you. We'll talk about that next time. I'll wrap up for today here. Let me give you your exams back. We'll call that quiz. Let me shut off this video.